Hi, I'm Joshua Carter. I'm an author of 5 books talking about different objects in outer space. This video is about how I, as a 16-year-old teenager, am able to make high-quality 3D visualizations of other terrestrial planets using free, ultra-high-quality datasets available online. Let's get started. So now I'm going to walk you through it. The absolute best website that I've personally found for finding public domain and free data is astrogeology.usgs.gov/search. And basically, if we go here, we'll have a massive amount of data that we can go through for all of the terrestrial planets. So, of course, we have gas giants here, but we don't have textures for the gas giants themselves. We just have textures for all of the moons of the gas giants. So Io, Ganymede, Callisto, etc. And so here I'm just going to use Mars since that's a very easy example. And I'm going to be downloading 2 things. So the first, I'm going to be downloading color. So we need color data to colorize the surface, right? And then the second is going to be height data, right? In order to make it actually look 3D. So I'll go to geospatial form and I will click global mosaic. And then for map projection, both of them are fine. And what you'll notice is that you'll have these 2 maps. So the Mars Viking colorized global mosaic and the Mars and this other one. And both of them are pretty good. This one is higher quality, but it does have some artifacts. So like you can kind of see a little bit of artifacts in the data itself. Whereas the other one is technically lower quality, right? Because it has a higher amount of meters per pixel, but it's much smoother. So you can clearly see the difference there. But both of these textures will work for the vast majority of cases, right? And if we actually scroll down, we can actually look at the resolution. And the resolution of this one is 23K. So more than enough for a global mosaic, and very good for even just large regions of the planet. So what I'm going to do is I'm going to actually scroll up and I'm going to process this data. So I'm going to go to process. And here you'll type your email. I'll just type my email here. You can have a job key. So if you ever wanted to save these settings and re-download stuff for later, you'll get a job key that you can reuse. For now, I'll skip it since I don't have a job key. File to process, that's already there. We can also create a job name and description. I'll just leave it as it is for now. Image options, so you'll have different filters and stuff depending on the data that you download, but in this case it's just RGB, so you can just leave it as all bands image. The output resolution in meters per pixel, so because I want the highest resolution possible, I'll just leave it as default. If you wanted like a certain resolution, so if instead of 23K, let's say you wanted 16K, you would just have to do basic math to figure out what the meters per pixel would be in order for it to be a 16K image, and then you can paste that number in, and then you'll be able to download it and it'll be exactly 16K. And so we also have projection. This is useful, especially if you're doing regions of the planet. If you want a global mosaic, the best projection will be equirectangular, so that way you can just map it onto a sphere without much issues. I'll just choose 0, 0 for the center, longitude, and latitude, and then I will just leave everything as it is. And then I can download a file format. Always choose TIFF. So we'll have different bytes. A good way to know which one will get you the highest quality for the space will just be to go over to the actual page itself and then see what its bit type is. Since the bit type is 8, that means I'm not going to get any more quality going up to 16 or 32, and so I'll just leave it at 8 for now. Make sure it says no stretch, and then add job. And then you can also monitor the progress of that job by clicking this monitor hyperlink, and then you will get the job key, so if you ever wanted to reprocess. And then once you have this finished, it'll show everything, and then you can download the zip file at the bottom. So now I'm going to do the same for creating the actual height values that will make it 3D. And so what I'll do is I'll go to geospatial form again, but this time I want digital elevation model. The only ones you should care about now are the MEX HRSC and the MOLA DEM. The HRSC data is data from the European Space Agency, and you have to give them attribution and redistribute whatever you use it for under that same license. I want to do commercial projects, and so what I typically use, I just typically use the MOLA data. And even though it's technically higher meters, so thus lower resolution, it's still plenty, right? We can scroll down and see it's 46K, which is absolutely massive. It'll be more than enough for large regions of the planet, or even reasonably small regions, right? And so we can just go over here to process and do the exact same thing, enter our email. We can skip all of these, whatever resolution you'd like, projection, equal rectangular, 0, 0 for the center, and then keep the maxes as they are, and then download it as a 16-bit TIFF, since over here we can scroll down, look, and it's 16 bits. So we can download as a 16-bit TIFF and then add job. And then we can come back to these whenever we'd like. Since I actually already have these, I'll actually just move directly to the next part. But you'll just have to wait however long, right, in order to see it get started and then ultimately finish. Okay, so now what I'm gonna do is I'm gonna normalize my height values. And the reason why I'm doing that is because the actual data set has negative height values, and Blender doesn't actually read those. So if I were to put it onto a sphere in Blender, only the height values that are above the Martian sea level would be able to render. So I'm going to have to normalize this file. So the way I like to normalize it is just by opening GDAL. So I'm going to go to Ubuntu. I'm going to take this file and I'm going to go to where Ubuntu is. So and then I will copy it and then paste it into here. Should take a little bit, but once it's done, I will basically paste this GDAL command that I have here. So basically GDAL is taking the lowest height value and the highest height value, and then it is just normalizing it. So going from 0 to 1, make this normalized, and then it will take a little bit to output, but once it's done, you'll be able to actually refresh in here, and then you will see the normalized file. And then you can go back to where you had your height values initially, and then just paste that file into that same folder to access it. So now I'm going to go to Blender, right? And as you can see from the File Explorer, now you're actually able to see the image. Now I'm going to go to General, just a general project. And I'm going to go to edit mode, and I'm going to subdivide this cube until I'm satisfied. So 7 or 8 will do. All right, so now that I'm done subdividing, I will do Alt-Shift-S to be able to make it into a sphere, and I will press 1 on my keyboard, and then I'll press Enter. And so now I can go back to object mode, and now it's a sphere. I'm going to go down here, and I'm going to click this little icon here, go to the shader editor, right? And in order to see the shader, I'll just go to this rendered viewport shading, and there we go. And so what I'm going to do, I'm going to actually delete this default BSDF, and I'll just make it diffuse. And so now I plug this in, and there we go, right? We have a sphere. Now all I need to do, I need to add a geometry, right? So I can actually reference the space of Blender, basically. So I'll take this geometry position node, and then I will do a vector math. So a vector math, and I'll do add, and then I'm gonna add 1, and then a vector divide, and then I will divide by 2. And the reason why I do this is basically when I have an image texture that I'm trying to put onto a sphere, I have to do this in order for it to actually correctly map onto the sphere. And so now I'll just get an image texture. I'll start off with the color mosaic. So I'll open that, plug this into here, plug it into the color, and then you'll be able to see the color mosaic on the actual sphere. It looks a little wonky though, and that's because it's on flat instead of sphere. So we gotta change it to sphere. And there we go. Now all we have to do is just make this from linear to cubic or smart. And that is it for the color. So to add a height, I will just add another image texture. The normalized TIFF, open that. So vector, plug it in there. And then I'll add the displacement, and then plug the displacement into the displacement, and then the color into the height. Nothing is showing up, and that is because we actually need to do a couple things first. So first of all, we need to go to the actual material, and then instead of bump only, make it displacement only or displacement and bump. The second thing we need to do is we need to actually change it from flat to sphere. And the last thing we need to do is change this from sRGB to non-color. And so now you'll actually be able to see a little bit of height, but to get that to really come out, we're gonna have to go to the scale and just adjust it a little higher. And that way you'll be able to really see like the actual scale. Of course, not too much or else it'll look weird, but just enough to where you'll be able to see like all of these different features. I'm actually gonna change the light. Instead of point, I'm gonna make it sun. And I'm gonna make it 5 strength. And then I'll change the angle to like 130 or something. I'm gonna actually change the angle of the sun just so that way we can see Valles Marineris. And now look at that detail. That is amazing. You're able to see some quite insane detail, like really insane detail, because of how good these data sets are. Like they're just fantastic. I use it all the time. I use these data sets. I use these data sets to create my visualizations in my most recent book. It's the quality of these data sets are just insane. It's just insane. Like genuinely, like just look at that. It's so cool. It's so cool to see this. And also for a last thing, especially if you get really close, select the cube, which is a sphere now, and make sure to shade smooth. But yeah, that's basically it. That is how I make these models. And oftentimes, if it's for a region of a planet, then I don't use a sphere. I just use a plane and then scale it at the proportions of the image or something. I would just put the image texture on the plane without like these nodes, just putting it straight into the position, and then that's it. Now, the one thing you need to be careful about is actually moving the sphere, because if you move it right now, it doesn't quite work. The main reason why is because we're actually taking the position of the world, which is why it's geometry. If we did texture coordinate and we chose the object, it would do the same thing, but I can move it, I can rotate it, I can basically do what I want with it, right? You can choose texture coordinate. I just chose geometry position because that's what I normally do unless I need to move things. And that is how I've created NASA-like visualizations of other planets. But there is just a little bit more to this. See, We didn't really work with raw data and then create a visualization from start to finish. Can we truly take raw spacecraft data and work through an entire pipeline using some of the most advanced planetary data processing software to date and create a true reconstruction of a planet's surface from scratch? Yes. Yes, we can. This video was merely an introduction to the general idea of visualization and 3D reconstruction. My objective is to create a series that finally brings planetary modeling to the public, creating a comprehensive guide from start to finish. This is going to require thousands of hours of diligent research, practice, and theory consumption in order to do this successfully, which is why I'm taking you on this journey with me. But for now, I'm Joshua Carter, and I will see you next time.